This lesson today, we're looking at integration by substitution. Essentially, this lesson will be about reversing that process of calculating the derivative using the chain rule. Okay, so integration by substitution is allowing you to reverse that process and find the integral of a composite function where there is a relative value as an external function. So I'll show you what I mean. So I want you to consider the derivative of a composite function. So we're looking at the derivative of y is equal to f of g of x. So that maybe we're looking at derivative of 2x squared plus 3 to the power of 5. So for example, we can see that there's an internal function here. If we were to find the derivative of a composite function, then it's a chain rule. So our chain rule will be dy dx is the derivative of the internal function multiplied by the derivative of the external function, keeping in mind that that bracket will always stay the same. So derivative of the internal, and this is the derivative of the external. So that's our chain rule. You may remember it as dy dx is equal to du dx multiplied by dy du. So same outcome, fix that u there. Now, if we think about the flip side, and this is what our focus is going to be on, if we're now looking at the integral, we're looking at the integral of this g dash of x multiplied by f dash of g of x with respect to x, then it should follow that the integral there will be the original composite function. Okay, and that's what this process of substitution is going to allow us to do. The easiest way to do this is we're going to look at this process through a couple of examples, and then we're going to step it out and we'll say procedurally this is what we're going to do. So let's start with a nice easy one, EG1. We're going to look at the integral of 2 sine 3x dot dx using substitution. Now, we could technically do this using the rules that were given in the previous lessons, but I want to show you this process of substitution. So substitution means that we have to define a couple of variables and utilize these variables substituting into the original to make it an easier integral. So the first thing we say is we let whatever the composite function, the function within the function, be equal to u. So let's say let u equal 3x. So this is the first thing that we're going to substitute. So this is our first one, number one. We're going to look at du dx. So the derivative of u will be 3. And we're going to rearrange this so we can put dx in terms of du. So du is equal to 3 times dx. And when we divide by 3, we get 1 on 3 du is equal to dx. And this is the second thing we're going to substitute in. So we should always have these two values to substitute every time we use the substitution method. So there they are, 1 and 2. So what we can say here is that the integral of 2 sine 3x dot dx is equal to the integral of 2 sine u dot 1/3 du. So we've made a fundamental change here. Our function is now in terms of u, and we're integrating in terms of u. So if we bring this 2 and this 1/3 in front, we've got 2/3 integral sine u dot du. Now, the whole idea here is that we end up with the simplest integral we can get, and obviously the integral of sine is very easy there. Integral of sine is negative cos, so we've got 2/3 multiplied by negative cos u plus c. And now we can put u back in as 3x. So we've got negative 2/3 cos 3x plus c, and that's our integral. Now, that should be the same if we use the old process. So technically, when we apply any of those rules where we have a linear function within, we're shortcutting this substitution method. All right, so we're going to look at one that's a little bit more complex. Okay, so when we look at this example, we've got the integral of 2x squared multiplied by cos x cubed with respect to x. Now we can't use this, we can't use any of our general rules in this scenario because this isn't linear within, and we've got this extra product out front. Now the way we determine if we're thinking about can we use substitution, if we identify what the internal function is. So see this one here, this is the internal function, and if there's a link between the internal function and the external product, a derivative link, then we should be able to do substitution. So if we look at this internal function, it's x cubed, right? The derivative of x cubed is 3x squared. Now I know the coefficient is different, but both being x squared, we should be able to cancel out the x squareds when we follow through this substitution process, and you'll see that in a minute. So the first thing we do is we let u equal x cubed. Second thing we do is differentiate, so du dx is equal to 3x squared, and when we rearrange to isolate dx, we get du is equal to 3x squared dx, and therefore dx will be 1 on 3x squared du. So here's our 2 points of substitution. We can replace x cubed with u, and we can replace dx with 1 on 3x squared du. So we're saying that the integral of 2x squared cos x cubed dot dx is the same as the integral of 2x squared cos u. So there's our first substitution, and the second one is replacing dx with 1 on 3x squared du. Now we should see here that x squared and x squared cancel. We can take the 1/3 and the 2 out front, so now we've got 2 on 3 integral cos u with respect to u. Now the final process is we can perform this integral. So 2/3 multiplied by the integral of cos, which is sine, plus c. So we have 2/3 sine. Now u is actually equal to x cubed, so we'll put that back in, plus c, and we've got our integral. So that is our process of substitution. Whatever the internal function is, it must relate to the external product. So you will have to make choices when you get to the more complex problems. So whatever you let u, there must be a derivative link that will allow you to perform the integration, with the process being trying to eliminate all the complexity and perform a very simple integral at the end before subbing back in. And that's it. That's our process of integration by substitution. So if we had to write this down as a number of steps, so process integration by substitution. First step is check to determine derivative link between internal function and external product. So if you can do that, then you can probably proceed. 2 is let the internal function be u. We then find du dx, and we isolate dx in terms of du. Fifth is substitute u and dx into the integral. 6 is integrate, and then 7 is substitute for u. So that's the whole process. So hopefully that makes sense. The idea is to simplify the integration and end up with something that you can integrate, devoid of the original extra product value. And that concludes the lesson. In the next lesson, we'll go through a few more complex scenarios, and we may even look at the idea of linear substitution, which is a slightly more complex process.